So welcome to this afternoon session. My name is Jochen Köhnemann. I'm the chair of this session. So I'm in Waterloo. So for me it's late morning, like for a few others. So we have two nice-looking talks in this session. So the same rules as always apply. So the talks are 25 minutes long, and there's 5 minutes in the end. I mean, plus minus a minute or so. If you as an audience member want to ask questions, you'll be muted. Please just use the chat room. I'll monitor that and I'll relay that to the speaker. Afterwards, we have a Q&A session. In the Q&A session, you can raise your hand and then you can unmute yourself as well. I was told I have no power, so I cannot unmute you. So you can ask questions then. Good, so let's get started. The first talk in this session is on continuous facility location on graphs, and it will be given by Stefan Lendl from TU Graz. Take it away.
Thank you very much. I hope you can hear me now. This is joint work with Tim Hartmann and Gerhard Wüginger from Aachen. And let me directly start by introducing the model. We are looking here at a problem on a graph, and we assume that our graph is connected and undirected, and then all the edges have a unit length, like in the graph above here. And in this model for facility location, we assume that we can place points or facilities on arbitrary points on the vertices and edges. So we assume also that we can place a red point like this one here, for instance, on the midpoint of this edge, and then it will have distance 1/2 to the left vertex here and 1/2 to the right vertex here. And of course, still after that, we can define the shortest distance between two arbitrary points in the standard way. So for instance, this point here and this point here have distance 2 + 1/2. Now, the optimization problem we want to study on in this model is the delta covering number. For this, we define a set of points like the red ones on the top here as delta covering if for every point in the graph, so every arbitrary point on the edges or vertices, there exists a point S in our set that we selected of distance at most delta, and delta is an arbitrary non-positive number. So somehow we want a facility to be close enough for every point in the graph. And then the delta covering number of the graph is defined as the cardinality of the smallest delta covering set. So we want to select as few facilities as possible that cover basically the whole graph. Now, what is known about this model, a paper of Megiddo and Tamir from the 80s proved that computing this delta covering number is NP hard for fixed delta equal to 2. So they looked at this specific case and showed NP hardness. And also they proved that computing the delta covering number is solvable in polynomial time if the graph is a tree. A related problem, the problem of delta dispersion, is basically the packing variant, where you want to have at least a certain distance between 2 points, was analyzed by Grigoriev, Hartmann, Wüginger, and myself last year, and there we proved different complexity results. But now in this paper, we analyzed this covering number. Let me give you an overview of the results. We obtained a complete picture of the computational complexity for every fixed rational number delta. So we assume delta to be a rational, A over B and fixed, and then the computational complexity is like follows. If delta is a unit fraction, so 1 over B, then we obtain a polynomial time algorithm for the problem. But as soon as the numerator is not 1, so for any other numerator, we show that the problem is NP hard. In addition, we also analyze parameterized complexity for this problem for the natural parameter, so the size of the delta covering set. And here kind of intuitively, one would assume that for small deltas, the problem is closer to kind of vertex cover. So we want to cover all edges with the points we select. And as soon as delta gets larger, the intuition is kind of, it becomes closer to covering all, the problem becomes more about covering all the vertices. So it might be closer to dominating set. And this intuition is actually true. And we are able to show that there's actually a threshold behavior for delta less than 3/2. We can prove that there is a fixed parameter tractable algorithm for this problem. And as soon as delta is larger or equal than 3/2, the problem becomes W2 hard. What's nice is that there is no intermediary phase of W1 hardness. So the complexity directly jumps from fixed parameter tractability to W2 hardness. Kind of the proofs of this W2 hardness results are basically, as the intuition tells one, based on different variants of dominating set for different ranges of delta. Now, for the MP hardness, the idea is that we prove some technical lemmas that allow you to show that for every rational A/B with A greater or equal than 2, we can kind of show that there is an equivalent NP hard instance in some other range. And this kind of technical proof gives you the NP hardness for all A/B. In this talk, I want to try to give you an overview of the ideas necessary to show the polynomial time algorithm for unit fractions and the FPT result. So let's get directly onto that. And for the unit fraction result, first observe that we can kind of get back to a completely discrete problem because we can focus on solutions of a special form. Namely,
there's a question in the chat room.
Okay.
So I'll read it. Is there an intermediary phase where we can get XP algorithm?
Sorry?
Is there
yes,
an intermediary phase so we can get an XP algorithm?
So basically, if we assume that, that's a good question. So if we can get an XP algorithm, basically yes, because let me think about this. If we have a fixed number delta, we can show that we only need, yes, we can kind of round, use our rounding lemmas to obtain an instance which has constant, to get rid of the denominator, and then we only have to select a set of size polynomial in the constant. So by trying all sets, but we never check the details here, but I think it's possible to obtain this, but we did not look into that. So we should maybe, but we didn't check the details here, but I think it's possible.
Thank you.
Okay, so let's look at the unit fractions now. And for these, we can show that we can focus only on very special types of solutions, which we can then find. Namely, those we can solve just the one covering problem. Since what we can prove is the following lemma. We can show that the delta cover of G is equal to the C times delta cover of G prime. For C, a natural number, and G prime, the graph where we subdivide every edge C times. So that's a rather easy observation, and this allows us then to go from 1/B covering to 1 covering. The second thing we can show is that we can always find an optimal 1 cover that has the following form. It selects only points on the vertices and on the midpoints of edges. And this basically follows from this first lemma and the second lemma, which shows that for arbitrary delta is A/B, we can always find an optimal solution that is to be simple, namely that where the distances on the edges can be written as fractions with K/L, and L is to be simple. So we can write them as A/2B. And for the case delta is equal to 1/B, this is then exactly what we want. This means we can select points on midpoints or on vertices. So now we have to try to find such a solution. And somehow these midpoints remind us of matchings, right? Because if we select points on the midpoints and the graph has a perfect matching, then the midpoints of the perfect matching would cover the complete graph. Exactly, you have distance 1, and if I place a point here, you cover everything up to here, 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 here. And if there would be a perfect matching, then this would cover the whole graph. So maybe a connection to matchings is there. So we look at maximum cardinality matchings. And for maximum cardinality matchings, there's the nice Edmonds-Galley structure theorem, which looks like follows. You have an arbitrary graph, and you define as X the set of vertices for which there exists a maximum matching that does not cover X. So for instance, in this maximum matching of this graph, this one matching vertex is not matched, so it's contained in X. And you can construct a maximum matching for all of the vertices down here where they are not matched. And then Y, the yellow vertices, are the neighbors of the vertices in X, and Z, the blue vertices up here, are the rest. And the nice thing about this structure is that on the one hand, you can find the structure in polynomial time using, for instance, Edmonds-Blossom algorithm. And on the other hand, you know a lot of things about this structure. What do we know about it? On the one hand, the components of X are all factor critical. Namely, you can remove any arbitrary vertex from these components, and the remaining graph contains a perfect matching. Then the components in Z, the blue ones, all contain perfect matchings. And in addition, for every maximum cardinality matching of the graph, we know that this maximum cardinality matching is a perfect matching in Z, in the Z component, in the blue ones, a near perfect matching, so a matching all but one of the vertices in the factor critical components, and all the vertices in Y, all the yellow vertices are matched by some edge connecting Y to X. So this is what we know about the structure. And now we can use this structure on one hand to obtain a lower bound on our one covering set, and on the other hand to obtain a polynomial algorithm that exactly matches this lower bound. So what we do is we further decompose our graph based on the Edmonds-Galley decomposition, and we denote by G0 the blue graph basically. Then we further split up the components in X into the components with at least 3 vertices and the other components which contain all just one vertex, like the light gray ones here. And then we define G1 as the bipartite graph given by X1 and its neighbors. So these are these 3 vertices in this example. And then for G greater or equal than 3 is the graph on the dark gray components, the factor critical components with at least 3 vertices, and C greater or equal 3 is the number of such components. So in this case, we have 2 such big X components. And now we are able to prove the following lower bound on the cardinality of any one covering set S. So if S is a one covering set, and we can assume by our result before that S is in canonical form, we have the lower bound, following lower bound. S is at least of size has at least the size of a perfect matching in G0, so of a perfect matching up here, then a perfect matching in the dark gray components. So here you have for every edge here a point, basically, plus one additional point for every factor critical graph. And then in our bipartite graph, we need vertex cover number many points in addition to cover it. And the basic idea to prove it, I do not have time to show all the details, is to split up this point space of this graph based on the decomposition. And we split, for instance, here, exactly on the middle, on the 1/2 point of every edge. And then we can prove that to cover that one covering solution S must contain at least, that covers this space, must contain at least mu of G0 points in this area. So this is what we can prove. And the main idea here is that basically every point can cover at most two half edge. Every point on a midpoint of an edge can cover at most two half edges of the matching edge. And also every point, basically that gives us the result, because every point that's on a vertex also can cover at most one matching edge. And combining those two things then gives us the lower bound here. And then we can do something similar for the dark gray components, and also for the bipartite graph here. We can construct basically based on a set S that is one covering for this bipartite graph. We construct a set C that is a vertex cover. And we do this in the following way, that we take just the points on vertices, and for midpoints on edges, we take the point on the incident X vertex. And this gives again one cover, vertex cover then. And this gives the lower bound. So you need at least vertex cover many points. So now I want to give you the intuition on how to construct now a one covering set of exactly that size. And what we do is we start again with the Gala-Edmonds decomposition, and for every matching edge in the blue components, we take the midpoint. Okay, so for all of those, we take the midpoint. This gives then exactly nu of G of 0 many points. Then for all matching edges in the big factor critical components, we also take the midpoint. So also here we do the same. Good. Then for midpoints on, on edges X, Y in the matching that match some vertex here in either yellow, so in Y, with some factor critical component in large component, we would take the midpoint again. So here, for instance, the midpoint. And if there are factor critical components, large factor critical components that are not matched by any matching to some Y vertex, we would just take this unmatched vertex. So this way we construct exactly C greater equal 3, no, not, yeah, exactly C greater equal 3 many points. So for every of these components, either the point of the incident matching edge or just the point itself that is not matched. And now for the bipartite graph, we compute a vertex cover, and we can compute it since it's a bipartite graph also in polynomial time. And the Y vertices of the vertex cover, we just keep. So if this vertex is in the vertex cover, we just take it in. For the vertices in the vertex cover which are contained in X1, we make a case distinction. Either in our Canelli maximum matching, there is an incident matching edge to this point. In this case, we would take the midpoint, and otherwise we would just take the point. And it's now, after taking this solution S, it's easy to see that this has exactly this cardinality, and we can check that by the properties of the Gala-Edmonds decomposition, and since delta is equal to 1, this is also one covering. Since basically we have taken always some close point to the Y vertices here, and the upper part, the upper half here, is already covered by the perfect matching up here. And this completes the polynomial time algorithm for one covering. And then for 1 over B, you just use the standard scaling argument from the lemma. So this can then also be constructed. So let me now move on to the FPT result for delta less than 3/2. And the first part here is again a matching argument. And this is the only point in this algorithm where we really need that delta is less than 3/2. And it's to prove the following lemma. If delta is less than 3/2, then the delta cover of G is larger or equal than the matching number of G divided by 2. And why is this the case? It's the case because every point that we select covers at most 2 midpoints of matching edges. So no matter where I place a point, it cannot cover more than 2 midpoints of matching edges. And this only holds true for delta less than 3/2. As soon as I have delta equal to 3/2, this does not hold anymore. And this is where this FPD argument breaks, exactly at this point. What do we get from that? We get from that for maximum matching M and K our parameter, it must hold that the cardinality of M is less or equal than 2K. And since every matching gives us a vertex cover of twice the size, we also have now that under this assumption, the vertex cover number is bounded by the parameter. So we are now in the regime of bounded vertex cover. And we can now use techniques for fixed parameter tractable algorithms when the vertex cover number is bounded, and obtain a reduction rule based on that. So here's the intuition on how to get this FPD algorithm now. We know that the vertex cover number is bounded by our parameter. And now, since it's a vertex cover, as in the example here on the right side, if we look at the rest of the vertices after removing the vertex cover, we have an independent set. This is the vertices on the right side here. And now what we very often do when using vertex cover is we basically look at neighborhood diversity. So we look at all possible subsets T of the vertex cover and define as I of T the set of vertices in the independent set that have neighborhood exactly T. So for instance, here in the example, if you look as T as the two blue vertices, then I of T is exactly the blue vertices here, since they have all neighborhood T. And the idea why we do this is because those vertices they can be many, but they all behave kind of similar. They are all very similar because they have the same neighborhoods, and we can use this in our algorithms. Good, what do we do next? We define as GL of delta the minimum size of a delta cover for the open ball around a vertex V, like this one, with distance 1 minus delta. So we select some vertex here in the independent set and look at this open ball, and we can pre-compute, since delta is constant, the number GLD delta, that's the minimum size of a delta cover that covers this part of the space. And why are we interested in that? We are interested in that because this is the part that kind of has to be covered from inside, because from inside the ball BV1, so the open ball, because a point on this vertex can only cover up to here and cannot cover the space inside here. So this is the space that has to be covered by points on the vertex and the incident edges to the vertex. And we can pre-compute those numbers. Then we define a vertex V in IT. So we fix now a capital T and look at the vertices in IT. And a vertex V in IT for any fixed solutions S of delta covering solution is called heavy if the number of points in the neighborhood of this vertex, so basically on the vertex and all the edges incident to it, up excluding the vertices in C, is larger or equal than this minimum number. So it's the number plus 1. And then we call this vertex heavy. In our definition, we define calligraphic B of T as this set that you are shown in red here. So it's basically all the vertices in IT and basically the union of all balls open balls BV1 for all V in IT. And then we look at the closest point. So for every T in capital T, we look at the closest point in S intersection calligraphic T to T. So we look for this and this point on the closest point of S. And this is S of T. And if S of T is on an edge to a vertex V, then we call V busy. And now we can observe that there can be at most size of T many busy vertices in I of T and size of T many heavy vertices in I of T, if S is an optimal delta cover.
You've got about 5 minutes.
Thanks. Okay, so now we have bounded the number of heavy and busy vertices, and we kind of observe that all the vertices in I of T that are not busy and not heavy are kind of not very interesting, because they have no influence on anything in the graph outside of their own region B minus V1. So there we know we can just place GL of delta many, GT of delta many vertices. So the idea now is, if the cardinality of I of T is larger than 2 times the cardinality of T, then there exists a vertex W in I of T that is neither busy nor heavy. So what we do is, if this is the case, we can just remove one of those vertices. And since all of these vertices are basically the same, we just remove any one of them. And we know that we have to decrease the parameter K by G size of T delta. And then we can continue like that. And after this process ends, we know we have an instance that is bounded by the size of the parameter. So we have a kernel. And there we can solve the problem. And this gives basically the fixed parameter tractable algorithm for the case delta strictly less than 3/2. So let me quickly summarize. We have obtained a complete picture of the computational complexity for all delta, namely if we have unit fractions, we have a polynomial time algorithm, otherwise the problem is NP-hard. And with respect to parameterized complexity with the natural parameter, we know that there is a transition from fixed parameter tractability to W2 hardness exactly at delta is 3/2. So let me finish here and thank you for your attention.
Thank you. Okay, we have time for questions. Are there any questions in the audience? Yes, there's one. Kartik.
So is the one covering algorithm so one can also think of it as splitting every edge with a new vertex in the middle and then trying to ask for some sort of dominating set. It's not really dominating set, but you're asking every vertex to be within 2 hops of the set that you choose. Am I right?
Yeah, I think. So you're saying, yeah, I mean, kind of, we could look at this special, I think it's kind of dominating set with, yeah, you can see it as subdividing the graph, and then you look at special graphs. So it's not a problem on general graphs anymore, but on graphs where kind of you have many subdivided edges, and then you place points there. And for one covering, you would have to insist on that basically, yeah, every vertex there is dominated.
It's every vertex is within 2 hops of the set that you choose, right? The dominating set says every vertex is within 1 hop of the set that you choose.
Yes. So,
but the reason it is solvable is because it's not an arbitrary graph; it's a subdivided graph.
So this would not be solvable for general graphs, and the reason it's solvable is really this kind of nice connection to the matching structure. So I do not have any other intuition why this is solvable in this other kind of equivalent interpretation.
So is there a polyhedral characterization and such for these, or is it just a reduction?
This is just a reduction. I do not know of any polyhedral characterization, but we have not tried to to get any also. So to be honest, we have not tried to do that.
Hi, I have one question.
Mm-hmm.
So yeah, if we look at the bipartite graph and similar like decomposition, like Edmond Glide decomposition, then we have this special property for this set Z that it is like independent set, right?
Sorry, yes, yeah.
Yeah, if you look the similar decomposition for bipartite graph, then we have this special structure that the set Z is the independent set. So I was wondering that whether that extra information can be used somehow to improve, or like, did you think about that?
So for the analysis, it doesn't really help much because basically the components in C you see here, they do not cause any trouble actually. So they are easy to handle from this analysis. What you get is of course faster algorithms since we use basically matchings as a maximum cardinality matching as a black box here. Mm-hmm. And in bipartite graphs, you can solve that more efficiently.
Okay.
Okay, so maybe we should move on. You're past the allotted time for questions. Let's just thank the speaker again.
Thank you.